Hello everyone, this is Professor Coppola broadcasting from the nation's capital, and in this review video I want to get you ready for exam number 2, which is going to cover chapter 13, chapter 14, and chapter 15. Okay, so here we are in slide 2 of chapter 13, the back and forth of equilibrium. Now, 3 important points about equilibrium which I'll repeat several times. When you reach equilibrium, the forward rate of the reaction is equal to the reverse rate. There's no change in concentrations of reactants and products once equilibrium is reached, and the concentrations of reactants and products at equilibrium are not equal to each other. Okay, now we move to slide 4. Okay, so the big secret that I let you in on is reactions go both ways. They go forward and they go in reverse direction. And you can represent the double arrow this way or any of these notations. Slide 5. So here I'm showing this chemical reaction here, N2O4 gas going to 2NO2 gas. And again, the 3 things that I just said. Forward rate is equal to reverse rate at equilibrium, no change in concentrations once equilibrium is reached, and the concentrations of each of these do not equal to each other at equilibrium. Okay, let's go to slide 7. Now remember, there's a difference between the macroscopic view and the molecular view. The macroscopic view, once equilibrium is reached, there's no color change. So here you have a certain amount of NO2. And you also have a certain amount of that. In the beginning, it's all N2O4. And at the end, it's mostly the NO2. So there's no change at the molecular level. However, at the macroscopic level, the color doesn't change anymore. But it's dynamic, that is, there's movement going on at the molecular level because the forward rate is going to equal to the reverse rate once equilibrium is reached. And so every time one of these breaks down to form two of these reform, and you get the product again. So it's dynamic. Things are happening at the molecular level. For every one that goes this way, one goes this way. But looking at it with the naked eye, you don't see any change. But at the molecular level, it is a dynamic equilibrium. Okay, let me introduce the equilibrium constant. Remember, I called this the big K, and there's several different kinds, as we learned in this chapter, and then we'll get the acids and bases. And it's different from the little k, which was the rate constant, which is something different. This is the big K. Okay, and then we go to slide 9. Remember, we indicate a little EQ, which means equilibrium constant. And essentially, it's the concentration of the products over the concentration of the reactants. Okay, slide 10. And these are all the different equilibrium constants that we looked at in these 3 chapters. And by the way, sometimes they just write it as just a K. It means equilibrium constant. I like to put EQ to emphasize it. Sometimes they put KC that refers to concentration, but it's the same thing as that. Or KP deals with pressure. And remember, we have an equilibrium constant for weak acids and weak bases and for water. Now, just so you know, if you have a problem involving pressures, everything is done the same way. You call it a KP because it's just going to be all gases, and you're given the pressure in atmosphere, and you just proceed the same way as if it was molarity. Okay, so don't be thrown by the fact that it's pressure. Everything's the same, done the same way. Slide 11. So, for any chemical reaction, the equilibrium constant is equal to the concentration of each product raised to its power equal to the coefficient over the concentration of each reactant raised to a power equal to its coefficient. And as long as the temperature is the same, this will always be the same. If you change the concentration of one and let equilibrium reestablish itself, you always get the same K. And then here's the actual example. So you would put the products, concentration of the products raised to 2 because the coefficient is 2 over N2O4. And very important, as we learned, only aqueous or gas are used in the equation. Okay? Substances that are solid or liquid are not included. So solids and liquids are not included, and they're just given a value of 1. So watch out for that. We don't include solids or liquids in the equilibrium constant because they're not solutions. Their concentration doesn't change. They're just a pure substance. And a concentration is a solute in a solvent. It's a mixture, a solvent, a solution. But a pure substance is, or like a liquid or a solid, is not a solution, so it's given a value of 1 and not included in our equilibrium expression. All right, here's another example. Explicitly tells you how to write the equilibrium expression, which is also called the law of mass action, which I don't like that name, as you know. It doesn't tell, because it's not very descriptive. But anyway, it is called the law of mass action. That's why you need to know it. And there will be a question on the exam where you'll be given an equation and identify which is the correct equilibrium expression. Okay, so you have to follow the rules. They have to be raised to the right power equal to the coefficient, same thing here, and then the reactants, the same thing. Alrighty, let's go at slide 12, slide 13. No, wait a second. I want to go to slide 14, I guess. Yeah, and this was a little practice. And the thing that we wanted to remember is that, like I was saying before, solids and liquids are not included. So you got to watch out, because like in an equation like this, you got a solid that's not included. You got a liquid that's not included. This means it would be pure sulfuric acid with no water at all, just pure. That's not included. So that, and this is a solid, so that's not included. And that's a solid, that's not included. Anyway, so that just emphasizes that you don't include solids or liquids in the equilibrium expression. Okay, now we're going to go to slide 15. Now remember, the bigger the K, the more products you have. Okay, so when K is large, you have mostly products because it's products over reactants. If K is small, you have mostly reactants, because that means this part of the fraction is very big. And so, therefore, the value of the fraction will be small because the bottom, the denominator, is big. Okay? So if you have a lot of products, K is big, greater than 1. If you have few products, K is small. Of course, in industry, you want to have a big K, so you get a lot of products. And this shows the same thing pictorially. This may help you just to see a picture of the same idea. And it's good to come at things from different angles. Okay. Now, there's three types of problems. One is the plug and chug, where you're given the concentrations at equilibrium and just plug them in. The second type, you got to determine which way will it move to reach equilibrium. And the third type, what are the equilibrium concentrations if you're given the equilibrium constant and the starting concentrations? And that's the most fun, at least for me, but it's more complicated. Okay, so let's look at a plug and chug. So this is a plug and chug that we worked out. Slide 23. Actually, it's slide 22, I guess. But you're given the starting concentrations. Excuse me, you're given the equilibrium concentrations. And I always recommend write out the equation and right below it write what the concentration is. And then you find the K sub A, you just plug in and do the math. Okay, so you may see a problem like that. All right, let's go to slide 28, I believe. And this is one involving pressure. Remember I said pressure, everything's the same, except instead of molarity for the concentrations, it's just going to be atmosphere. So everything is set up the same. And here's a solution. Whoops, I don't have the solution on that page. Yes, I do. Okay. So these are the equilibrium concentrations, and then you just plug them in the same way. So that would be slide 27 and slide 28. Okay. Then we go to reactions that are not yet at equilibrium. And the question is, which way will they shift to reach equilibrium? All right. Okay, so then we have to deal with something called reaction quotient, and we call it Q. A quotient just means one number divided by another number, and that's what we have here. And the difference between Q and K, they're basically the same, except this is at equilibrium and this is not. And so we want to see which way will the reaction shift to reach equilibrium. Okay. Let's see here. Okay. So this would be a case where you're given the concentrations and you have to find the Q and determine which is bigger, Q or K. So like in this case, so it's not at equilibrium. You're given what the equilibrium constant is. For the data given, again, it's not at equilibrium, you find the Q. Since the Q is so big and it needs to reach equilibrium, it's going to end up with a smaller, much smaller. Well, how do you do that? Well, you got too many products, so it's going to have to shift left in the equation. It's going to have to shift that way. Okay, so you need to be able to do that type of a problem. Which way will it shift to reach equilibrium? Okay, let me see here. And then we have a little pictorial view. Here's our equation. All right. KEQ and Q have the same expression. This is at equilibrium and this is not. So if K is bigger than Q, then it's going to shift to the right. If Q is bigger, as we just saw, it's going to shift to the left. And if Q is equal to K, that means it's at equilibrium. Okay. Alrighty. And then let's go to this little piece of wisdom. When all else fails, think. So you have to think your way through the problems. You know a lot of information. And if at first it doesn't come to you, just relax, take a deep breath, and think. Maybe come back to it later, and as I say, your default mode of your brain keeps working on that problem. So when all else fails, think. Don't panic. Alrighty, let's see now. Yeah. So here we have a little cheat sheet, review sheet. Again, looking at these equations and what I just said, if Q is bigger than K, it's going to shift left because there's too many products. And so this has to get smaller for Q to approach the value of K. On the other hand, if the equilibrium constant is bigger than Q, that means Q is smaller, we have too many reactants, so it's going to shift right. And again, if KEQ is equal to Q, then you're going to be at equilibrium. Alrighty. then we're going to go to the type 3 problem. Okay, in the type 3 problem, you're given the equilibrium constant, you're given the reaction, and you're given the starting concentrations, and you're supposed to determine what will be the concentrations once each equilibrium is reached. And so you set up our ICE table or RICE table. So here's our reactant, here's our product. Let's say you were told that you're starting with 0.8, and before you start the reaction there's 0 there. Then a certain amount of this gets used up. But because the ratio is 1 to 2, that means twice the amount of X is formed. So we add these up, and we get 0.8 minus X, and we get 2X there. And so then we substitute in these expressions, 2x squared over 0.8 minus x equals that. Now, this particular example, you're going to have to use the quadratic equation. I'm not going to make you use the quadratic equation to solve for x on the exam. So if you were faced with this on the exam or on the standardized test at the end of the year, we can assume that x is so small that we can call it 0. A very, very small amount actually gets used up. So we can make that assumption, and that way we don't have to use the quadratic equation. Now, whatever is used up here, we get twice the amount, so we'll just call this 2x. We add these up, so we get 0.8 and 2x. And now here's our expression. We don't have to use the quadratic equation. So we do the math, and eventually we're going to get x is equal to 0.03. Now if x is equal to 0.03, then for NO2 it'll be 2 times x, which is 0.006, will be formed. And we're saying that approximately 8 molar, only 0.8 molar, I mean, you started out with that and that's what you end up with. So basically you're saying almost none of it was used. Okay? So we can make that assumption. In reality, actually 0.03 was used. So it would actually end up at equilibrium as 0.77 molar. And that's if you use the quadratic equation. Alright, so we assume this is 0 just so we can avoid the quadratic equation. Alright, on this slide, which is slide 49, it's a very nice picture to help you of those 3 properties that I told you that occur at equilibrium. Once you're at equilibrium, concentrations of reactants and products don't change anymore. But it's at a dynamic equilibrium. Every time one goes this way, another one goes that way. And so the net effect is there's no change in concentration, and you can see the concentration of the reactants is not equal to the concentration of the products. And now we go to slide 50. This is just a review. Here's our equilibrium expression. And just reviewing what I said before, large K means the forward reactions favored, you get a lot of products, which is the C and D. If you have a small k, that means the reverse reaction is favored, and you have a lot of reactants. Okay, now we go to slide 51, and we're going back to type 3 problems again, but this time it's called a perfect squares problem, and you don't have to use a quadratic equation. So I gave this example. You're given the KEQ, you're given the initial concentrations, 0.2 and 0.2. Now, by the way, in this particular case, they made you compute that. So they said 0.4 moles in 2 liters. So 0.4 divided by 2 liters is 0.2, so it's 2 molarity. Okay, Let's go to the next slide. And so, I know there's a lot on this slide, but so we're starting off with it. Here's our equation. We got the KEQ. Here's our Rice table. The initial concentration is 0.2 and 0.2. That's before the reaction starts, and so there's 0, 0. And then there's going to be a certain change, X. Some of this H2O will be used up, and the same amount of that will be used up in terms of moles. So we call it X. And since it's a 1 to 1 to 1 ratio, for every X that's used up, you get an X formed for each of these. When you sum them up, you get 0.2 minus X, 0.2 minus X, X, and X. Here's our equilibrium expression. And so now we substitute in these values. So X for the products, 0.2 minus X, 0.2 minus X for the reactants, and look what we have. X squared over 0.2 minus X squared equals 49. We take the square root of both sides, and then we solve for X. But we're not done yet, because X is how much was used up of the water. Start with 0.2 minus 0.175, we get that number. The same thing here, and over here X is 0.175, so we get 0.175, 0.175. And if you wanted to double check you did it right, all you do is put these numbers into this equation and you will get 49. Okay, here's another perfect squares problem. You can look through it yourself. The one thing that's interesting about this is now we've got, for every one of these that gets used up, we get twice of that. So that's why we end up with a 2x there. And so I solve it there for you, and then we go to the next slide, and then we actually put the actual numbers in and find out what the concentrations will be at equilibrium. Okay, that brings us to Le Chatelier's principle. This is slide 59. When a chemical system at equilibrium is disturbed, it reestablishes equilibrium by undergoing a net reaction that reduces the effect of the disturbance. It's going to relieve the stress. What are some of the disturbances you can get? Change in concentration of reactants or products by adding or removing them. Change in temperature by adding heat or removing heat. And again, we're going to think of heat as a reactant or a product. We actually put it right into the equation. Or a change in pressure. And you can change pressure by increasing or reducing the volume. So here's the little device I gave you to help you to figure out these problems. So if you somehow change the system at equilibrium, it will shift left or it will shift right to offset the change and reestablish equilibrium. And when solving Le Chatelier's problems, think either replace, when I say replace I mean replenish what was lost, or consume it to offset the change. Okay, now I move to slide 77. Now prior to this slide 77, I give lots of examples of Le Chatelier problems. This slide is very nice because it summarizes things very well, neatly, and you should try to solve it by covering this column up. Notice here, because it's endothermic, we're going to put heat on that side of the equation. If it was exothermic and a negative, then we put heat on the other side. So when we add N2O4, it's going to shift to the right to consume it. When we add NO2, it's going to shift to the left to consume that. If we remove N2O4, it wants to replenish it. So to do that, it has to shift left, and that's what we have here. Removal of NO2, same thing. We remove NO2 to replenish it, it's going to shift right. If I add helium, it's not part of the equation, it's going to have no effect, so no shift. Now remember, I can either say I increase pressure, or I could say I decrease volume. When you decrease volume, you're increasing the pressure, In that case, it's going to go toward fewer moles to offset that pressure, because fewer moles have less pressure. So we have 1 mole here, we have 2 there, so it's going to shift left. On the other hand, if I increase the volume of the container, it's the same thing as decreasing the pressure. Now the stress is a decreased pressure, so it wants to go to a condition where there's more pressure. To make up for that, here's 1 mole, here's 2, so it's going to shift to the right. If you increase the temperature, you should think of that as adding heat. So we put heat, we think of heat as a reactant. If I add heat, then it wants to consume it, it'll shift right. If I decrease the temperature, that's the same thing as taking away heat. So if I take away the heat, it wants to replenish it, and so it's going to shift left. So this is a good review for Le Chatelier's principle. Okay, here's slide 79, sort of a wrap-up of what Mr. Le Chatelier discovered. By observing many chemical reactions at equilibrium, he could predict which way the reaction would shift after the disturbance. So he basically discovered the way nature behaves. When you add or remove reactants, at a equilibrium system, increase or decrease pressure, or increase or decrease temperature. Okay, then we move to slide 81. What effect does a catalyst have on equilibrium? Well, first thing you should know, and there might be questions on this, a catalyst has no effect on the equilibrium constant. All it does is allow you to reach equilibrium faster. Okay, so it speeds up both the forward and the reverse reaction. It has no effect on the K. You just reach equilibrium faster. So those are the things that I wanted to highlight for the chapter on equilibrium. Of course, you should go over all the slides and you should know all the terms, but I just wanted to try to guide you and highlight the things that are most important. Now we're going to move to chapter 14. Okay, so here's chapter 14, acids and bases. And the thing that I want to highlight here is the definition that you should know is the Bronsted-Lowry definition, that an acid is a proton donor, a base is a proton acceptor. Okay. And slide 3 just repeats the same thing. And because we had the Super Bowl, you could think of it as a soccer ball or football. The quarterback is the acid. He throws the football to the receiver, the base. So the acid gives away the proton and the base receives it. Let me go to slide 6. And we learn about 2 new equilibrium constants. K sub A, which is for a weak acid, and K sub B, which is for a weak base. And so, as we saw, I just took a drink, that's why I said excuse me. The weak acid and weak base are going to follow the principles of equilibrium, and that's why we call them an equilibrium constant. And we go to the next slide, which is slide 7. And what I highlighted here is, in general, the larger the Ka, the stronger the acid, because you have more hydronium ions, okay? So the top of the fraction becomes bigger. So in general, the larger the Ka, the stronger the acid. And this only holds, of course, for weak acids. We don't have equilibrium constants for strong acids. And so here's our strong acid. I'm not showing the water. It's a one-way reaction. It's not equilibrium. H plus Cl minus, one-way direction. Now sometimes you're going to see they'll show an equilibrium constants, but it's huge. It could be like 10,000. So basically we're saying it's one way. We just simplify it. So the strong acids and the strong bases, they're not in equilibrium, and they just go one way. Okay, let's go to slide 10. And then we talked about oxyacids, and you said if they have more oxygens and the other two elements are the same, the one with the more oxygen is a stronger acid. And these are just some examples. And I give other examples in the next several slides. And then we're going to go to slide 13. Okay. You need to memorize the strong bases. If it's not on this list, it's not a strong base. And they're easy to remember. All hydroxides have group 1. Group 1, LiNAKBCS. So you have LiOH, NaOH, KOH, RbOH, and CSOH are strong bases. And then the lower three in column 2, and again we can think of our old friend Castrobear, that memory device, calcium, strontium, barium. When they combine with hydroxide, they are strong bases. Remember, because it's in the second column, it forms +2 ions. Hydroxide is -1, so you need 2 of them. Okay?